We are going to be looking at internal resistance today. So this is technically a matric topic, but we don't really have enough time next year to cover it, so we cover it in grade 11 at the school. So you're not going to find this in any grade 11 resources that you might be using, okay, if you're using other resources. If you want to find extra resources on internal resistance, you're going to have to look at matric work. Okay, so firstly, before we get going with internal resistance, I need to speak to you about the difference between potential difference and EMF. Okay, and that's got to do with whether something is supplying energy to your circuit or whether it's taking energy out of your circuit. So we've been talking about voltage, right? We've been talking about potential difference measured in volts since we started circuits in grade 10. Anything measured in volts, we've called it potential difference. Now here comes the difference. Okay, so the potential difference, if you've got something like a resistor, right, this removes energy from the system. It uses up energy, okay? So anything measured, any difference in voltage from there to there over a component that removes energy is potential difference. Okay. Now, the difference between something that removes energy and something that adds energy to the system. Here, it's a little bit tricky. If we just chuck a voltmeter like this over our battery, what we will be reading is we will be reading the potential difference of the circuit, right? What from now on we're going to be calling V load, the terminal potential difference or the potential difference of the entire circuit. So it's almost like we're kind of looking at it inside out. Okay, this is attached not over the battery but over the whole rest of the circuit. Now, when we talk about internal resistance, we now have to look inside this battery. And inside this battery, because this is now we're trying to make it more like real life and less just, what's convenient to us to do the maths, convenient for us, sorry, to do the maths. In real life, your battery, the materials that your cell or that your battery is made of, that material actually also has a resistance. It will slow down the current moving through it, okay? It's not ideal. There's nothing in the world that has zero resistance. Okay, so with our batteries, we actually have within the battery a small amount of resistance. Okay, so this whole thing now is our battery. And the difference between energy in and energy out, so i.e. EMF versus potential difference, is that here, if we, at this point, were to measure the potential difference over the whole thing, this would be potential difference, and it's the terminal potential difference, or same thing as this, now we call the load, V load, okay, the potential difference of the whole external circuit, that's what the load means. But if you look inside, the reason it's potential difference is because in getting from this point all the way around the circuit back to this point, we will be taking energy out of the circuit. We'll be using energy up, right? But if we look just at the energy producing cell, if we look just at the cell, if we somehow try and ignore this tiny little resistor that's part of the battery, here, if we could, we can't, but if we could put a voltmeter just across that, this would be measuring something called EMF, okay, and symbol is it's not a capital E, it's like a backwards 3 looking thing, okay. So the EMF is what we call the potential when the potential is being supplied to the circuit, and that's just over the supply over here. Okay, so this is when energy is supplied to the circuit. Okay, so the EMF is across the thing supplying the energy to the circuit, and then the terminal potential difference is across this. Now this voltmeter and this voltmeter will not have the same reading because of this little resistor here. Okay, and I'll explain how all of that works now. So I'm going to erase this. And we're going to look inside a cell and see how does it all affect the maths. Okay, so just quick, there's something in brackets that shouldn't be in brackets. Brackets sort of normally implies it's like an add-on and it's not that important. It is very important. So where is it? Okay. So it says energy in and energy out, your big heading. Then there's two bullet points. And underneath each bullet point, there's something in brackets. It's very important. So devices taking out energy have a potential difference. And very important here, a voltmeter connected over a battery will measure the circuit potential difference if current is flowing through the circuit. So if you have a switch that is closed. Okay, that is important. And the fact that if we look at the second one, a voltmeter connected over a battery will measure EMF if current is not flowing through the circuit. So in other words, if we have an open switch. Okay, important that you do actually know those two things. Okay, now if we look at internal resistance, I'm not so much going to look at what it used to look like. We're going to deal with what it looks like to us now. Okay, so if we have a circuit, there's our cell. Here's our little internal resistor. We label that with a baby r. Internal resistance within a battery is a lowercase r. And let's say we've got, it might not be just one resistor, it could be a whole bunch of resistors, but we've got the equivalent external resistance of R, and I'm going to call it R load. Okay, and then over R load, we have a voltmeter that will measure V load, okay, the load potential, i.e. the external potential difference, which will actually be the same value as a voltmeter measured here. So this is V terminal, and V terminal is equal to V load. Okay, so that's sort of the same as how we've been seeing circuits so far, that the potential over the circuit is equal to the potential of the circuit, right? Now what's different is what's going on in here. Okay, so inside this, I'm not going through all the definitions and all those quickies, so you can read all those notes for yourself. I'm just going through the maths and why the maths is what it is. Okay, so if we look inside our battery, okay, so this, where's my green? This is my battery. Inside my battery, I have cells supplying current, or rather supplying energy in order to get my current going. And then I also have internal resistance. Okay, now within my cell, if I want to work out the EMF, if I want to work out, remember the EMF is the actual energy being supplied by this cell. Okay, let me actually just start off by saying, when you have a battery that says it has a specific voltage, okay, if you attach that battery to a voltmeter and you run it, you will actually, your reading will be lower than the voltage that the battery says it has. And that is because in leaving the battery, as the charge leaves the battery, it's going to lose some energy in the internal resistance. So that by the time it gets to the external circuit, it now has less potential energy, lower potential difference, than it says that it should have. Okay, so what happens is that the V, I'm actually just going to write a little note about that. Okay, the V on the label of the battery, to write it like a sentence rather, the potential difference on the label is the EMF. Okay, but if you were to actually measure the potential difference of a battery, you won't get the EMF reading, you're going to get a lower reading. And the lower reading is because of this internal resistance. Okay, so the actual V reading would be lower. And the reason for that is because some volts are lost within the battery itself. Okay, so some of that energy is being used up within the battery, and we call those the lost volts. Okay, so in getting out of my battery, my current's moving out of here, has to go through this tiny little resistor, and the volts that are lost through that resistor is what is the difference between what the EMF of the battery should be versus the potential difference that's actually getting to the rest of the circuit. So for this, if you ever want to work out how many volts are lost within the battery, we can just use Ohm's law. Okay, V lost equals the current in the circuit, the current out here is equal to the current in here because it's in series, okay, multiplied by the internal resistance. So this is our first important formula for this section. If you want to work out the lost volts within a battery, it's current times internal resistance, and this is not on your formula sheet. Okay, this is just Ohm's law, V equals IR, but it's Ohm's law applied to your tiny little internal resistor. So not on your formula sheet, you need to remember that. V lost is equal to I times internal resistance. Okay, baby R is internal resistance. Okay, then the next equation that we're going to use is important. It's based on the fact that the EMF, okay, which is what the battery says it can produce, the voltage that it says the battery is actually not the voltage that you're going to get. The voltage that you read on your external circuit plus these lost volts will give you the EMF, okay? Because you've got your EMF, you lose some volts, and then that gives you your external circuit potential. So the EMF is equal to the lost volts plus V load. Remember, V load is just the external potential difference. Let me just write here. V load, V external, and V terminal. These are all the same thing. Not just the same number, they literally refer to the same thing. Okay, it's the potential that'll be measured over the whole circuit. That's what all of those things mean. Okay, so the EMF is equal to the lost volts plus V load. Okay, so this is very important. This is like our starting point. Okay, now from here, we can expand depending on if we want to expand, if we know enough information here or enough information there. So, yeah, I'm going to show you how each of them can be expanded slightly differently to how it's done on your page. Okay, so V lost, we've already seen that can be expanded like this. Hey? So this can become IR. V load, this can be expanded to be the current times the load resistance, i.e. the external resistance. R load just means external resistance, the total resistance of the external circuit. Load just means external now. Okay. Yes, and V lost, I've got it there, but let's just do it here again. V lost is equal to I times internal resistance. So that means that this can be expanded fully if you want to. You don't have to expand it fully. You can expand one term or the other term, but it can be expanded fully into I times baby R plus I times R load or R external. And these currents are the same value, so you will also sometimes see it as E equals current taken out as a common factor, internal resistance plus load or external resistance. Okay, now in terms of your formula sheet, I just want to double check. Okay, in terms of your formula sheet, of these formulae, this down here at the bottom is the only one on your formula sheet. Okay, I have again attached a copy of your formula sheet and highlighted the ones that are applicable to this section. The only internal resistance formula on your formula sheet is this one at the bottom here. So it's very important, in my opinion, the main important ones are these two, and these are the two that aren't on your formula sheet. Okay, so V lost equals I times internal resistance, and EMF is equal to V lost plus V load, which is just your external potential difference. And then you would expand those as required until you get to this thing that is on your formula sheet. Okay, yeah, obviously have not spoken about everything that's on your notes, the theory kind of things, the definitions, that sort of nonsense, you must just read yourself. I'm more interested in making sure you understand the maths, where it comes from, how to apply it. So I'm going to pause you there and we're going to do an example, and then we are done with circuits. Oh no, guys, you didn't see the bottom of this at all. This is so annoying. Sorry. Okay, so this here, we took this equation and we expanded it according to these two. So for V lost, we said I times R. For V load, we said I times R load. And then we took out current as a common factor. Okay, so we took out our capital I, and then in brackets we've got internal resistance and the external resistance of the circuit. Okay, so now I'm going to pause you and then we can do an example. Okay guys, so we've got two examples. Example 1 there on the left says we need to determine the internal resistance of a battery with an EMF of 12 volts and a terminal potential difference of, I've written something down there wrong. The potential difference should be 18 volts. Potential difference is 8. Oh, sorry, I'm reading question 2. Sorry. Terminal potential difference of 10 volts. Sorry. Okay. And they give us that the current is 4 amps. Okay, so we need to determine the internal resistance. Okay, so options here are either we can work out the lost volts somewhere, they don't ask for that though, or we can use the EMF formula. Okay, so the EMF formula goes EMF equals, now you can go straight to the sort of the final form of it, which is the one on your formula sheet, but that's not necessarily always going to help us. So I like to start at the beginning. I like to start from the basics, which is that EMF is equal to the load or the external or the terminal potential difference plus the lost volts. Okay, and then I expand depending on what I know and what I don't know. I know EMF, so I'm keeping EMF. Do I know the load potential? I do. It's 10 volts. They tell us that that 10 volts is the terminal potential difference. And remember, V load, V external, V terminal, those are all the same thing. Okay, so we do know that, so we're going to keep it V load. V lost, we do not know the lost volts, so we need to expand V lost. This is the second important formula, that V lost is equal to I times R. Okay, current times internal resistance. So this is I times R. Now let's check. I know EMF is 12. I know V load is 10. I know the current is 4 amps. I'm looking for R. Beautiful. So I can sub it and solve. So this is 12 equals 10 plus 4R. Hop them over, subtract them. 2 equals 4R. Divide both sides by 4. And we get that, oops, sorry, this should be a lowercase r. And we get that the internal resistance is a half, hey? It's 0.5 ohms of internal resistance in the battery. Okay. Then example 2 is more like something that you would see, an actual circuit diagram. So this was just to get a taste of it. Okay, so a circuit diagram. And we've got 2 resistors in parallel connected to a battery, and we've also got a voltmeter connected across our battery. Okay, inside our battery we also have internal resistance. Question A, they want to know the current through the cell. Now we know the resistance of each of our resistors, and they've told us the terminal potential is 18 volts, right? So to find the current through the cell, because we don't know anything about current, we're going to have to use Ohm's law. We're going to have to use the fact that the terminal potential difference, or the load potential difference, or the external potential difference, whatever you want to call it, I'm going to just stick with V load, is equal to the current through the battery times the total external resistance. Okay, now the total external resistance, we don't know. We know the current. Do we? Oh, we want the current. Sorry, we know V load is 18. We want the current. We're looking. We still need then to find the load resistance, but that's not going to be too hard because we know the resistance of each of these. Okay, now the way I've done it on your notes is I've split it into 2. On here, I'm going to just chuck it all into one calculation. So I'm going to expand. That's my favorite word. Okay, V load equals I times R load. These are in parallel, right? The total parallel would be 1 over R1 plus 1 over R2 inverted. That's how we would find the total parallel resistance. Now we can substitute in. So V load is 18, current is what I'm after, 1 over R1, that's 1 over 4, plus 1 over 12, inverted. Okay, we can work this out and then divide both sides by that value. And once you've done that, you'll find that your current is equal to 6 amps. Okay, that's question A done. I'm going to have to erase this side of the board. I need the space. Okay, because question B then wants to know the current through each resistor. Okay, and again, I'm really diverting today. Again, I'm going to show you a different way to the way that it's done on your worksheet. Okay, so on your worksheet, the way that they did it, or on your note rather, the way that they did it was, they said, well, I know that that's 18 volts. Why does it look like so much? Oh, it's not. Okay, we know that that's 18 volts, so that must be 18 and that must be 18, because that's how potential difference works in a parallel circuit, right? So if you know the resistance and you know the potential, you can find the current using Ohm's law. Okay, so that's not too bad. So I want to show you a different way of doing it. Okay, ratios. We're going to use a ratio. Oh, let me actually first write the question. Okay, question B. We're going to find the current through each resistor. Okay, I'm pretty sure I showed this to you last year. I don't love it because it doesn't always work and it can get a little bit tricky, but it is quite nifty. It's quite a nice little trick to have up your sleeve if you need it. It is perfectly acceptable in an exam. You are allowed to use this method. Okay, we're going to be using the ratio method just for fun, just to show you how it works. Okay, so when you're doing the ratio method, you need to remember the fact you can only use this to determine current, and you can only use it when you have 2 parallel branches. Okay, it doesn't work for 3 branches. You can only use it to find current, and you can only use it for 2 branches. Got it? Okay, now you need to remember that current will split so that more of the current will go in this R1. More current will go the way with least resistance. So more current will go up here and less current will go down there. And proportionally, the way that it splits is an inverse proportion relationship, right? The lower the resistance is, the more current will go up there, and it will be proportional as well. So whenever you're dealing with proportionality, you can use ratios. So this basically means that if the resistance of R1 to R2, that ratio is 4:12, which we can simplify to 1:3, right? Then that means that the current in branch 1 to the current in branch 2 will be the other way around. Inverse will equal 3:1. So for every 3 amps that go up branch 1, 1 amp will go up down into branch 2. Okay, so this is what we're using. This is the logic. Now in terms of the method, the little recipe that you can use, if you want to know the current in branch 2, you're going to say that is equal to the total current multiplied by the resistance in branch 1 over resistance in branch 1 plus resistance in branch 2. Okay, it's a little bit tricky. And if you want to find the current in branch 1, it's the total current multiplied by the current in branch 2 over the current in branch 1 over the current in branch 2. Okay, so either way, you're taking the total current, you're multiplying it by a fraction, where at the bottom of the fraction, you've added together the resistors, and at the top of the fraction, you use the other resistor. So branch 2, I use the resistance in branch 1. In branch 1, at the top, I've got the resistance in branch 2. Okay, so I'm going to actually just quickly go ahead and do these. So for I2, that means total current is 6 times resistor 1 is 4 over 4 plus 12. Where's my calculator? Oh, here it is, sorry. Okay, so we're going 6 times 4 over 4 plus 12 is 3 over 2, 1 comma 5. So the current in the second branch is 1.5 amps. Is that what we got here? It is 2. Okay, same answer as we got on the worksheet. Now we're going to do the same thing for branch 1. Okay, so for branch 1, we're going to take the total current multiplied by the resistance in branch 2, which is 12, over the resistance in branch 2 plus the resistance in branch 1. So that's 4 plus 12 again. And we're going to get 4.5. Let's quickly check. 6 times 12 over 16 is 4.5 amps. Okay, let's just double check. 1.5 plus 4.5 is 6. Okay, and remember the current in your two branches should add to your total current, which is 6. So it works. Okay, so if you like using this, you can go ahead and do it. I don't mind. I think it's pretty cool. I won't lie. I think it's really nifty, but if you don't like it, that's fine. I don't often use it. I tend to just stick to Ohm's law. So this is the logic. This is sort of the rule. Okay, so if you want to use this ever, this is what you're going to use. You're going to remember the stuff I've put a little cloud over in red. Okay, so that's question B. I'm going to have to erase this, so let me just write down what was our current, 6 amps. Okay, so I total is 6 amps. The current in branch 1 was 4,5 amps, and the current in branch 2 is 1,5 amps. Okay. Okay, then question C is, okay, they tell us that the internal resistance is 0.375 and they ask us for the EMF. Okay, so I'm just going to write down those two pieces of information. The internal resistance is 0.375 ohms and they ask us what is the EMF. Okay, so as soon as you ask for EMF, you're going to go ahead and write the EMF formula. Not the one on your formula sheet, unless you want to. You can use that one and then try and work backwards to a point where you can substitute in. I prefer to start at the beginning. Okay, so EMF equals V lost plus V terminal or V load or V external, whichever one you prefer. And now we can expand. So we don't know E. We're looking for EMF, right? We don't know V lost, so we're going to expand that to current times internal resistance. We do know V load. That's this 18 volts that was given to us. Okay, so we're going to keep that as V load. Okay, and now we're at a point where we can substitute in and solve. So we're looking for EMF. EMF is current, which is 6, times internal resistance, which is 0.375, plus V load, which is 18 volts. And we get 6 times 0.375 plus 18, which is 20.25. Is that what I got there? Yes, it is. Always just double check with me. 20.25, and EMF is also measured in volts. Okay, and that's it. So I know this can get a little bit tricky, this internal resistance. Basically, it's just this formula really that's new. The other one, the one that says V lost equals I times baby R, that's just Ohm's law, but inside the battery. So the volts lost inside the battery as a result of the internal resistance. Okay. Yeah, and that's it. You've finished. You basically finished with circuits. Everything you're ever going to learn about circuits in high school. This is it. You're done. That was matric circuits. Well done, guys. If you get stuck, please do ask me. Yeah, let me know if you need me. Good luck with that worksheet. And it looks like we're going to take a bit of a gap next week. So I will only really talk to you guys again after the 1st of June. Well, I mean, I'll talk to you, but I'll only really give you more work after the 1st of June. Okay, enjoy. Cheers.